So why don't we get started? I want to first show you a small modification I made to the notebook from last class. Oh, I forgot to bring it over. There it is. So this is the notebook from last class, and I just said I would add one more picture. So we had some data set. We trained a linear SVM on it. And then we changed it to this other space by replacing each feature with that feature squared. And then we saw this picture, which is that in that new space, the data were linearly separable. And I just said I would add one more picture of what does that look like in the original space, which is this. So that's now posted, hopefully. And the main idea, again, from last time is if I do some transformation to my features and then fit a linear model, then that corresponds to something nonlinear in the original space. And so I can fit interesting boundaries. And then the kernel trick was a way of making that very efficient and also a way of specifying the feature transformations through a kernel function. So we had said last time it should be an ellipse, and it is. So that's reassuring. I guess no admin slide today. Okay. Today we're going to talk about stochastic gradient descent. So today is another optimization algorithm lecture. We only have 2 of those in the course. We already had one. We talked about gradient descent. Today is the other one, stochastic gradient descent. This is a very popular algorithm, so it seems worthwhile to include it in the course, although, again, all these things are maybe a little controversial. So here is the idea. Pretty much every loss function we've looked at in the course involved a sum over our training examples. So here's the squared error, but whatever loss function we were talking about, every training example got to have a say in how well we were doing. And the question for today is, well, what if n is huge? That is the case where stochastic gradient descent comes in handy. Well, now to compute the loss, or as we'll see, the gradient, involves this sum over n terms. And what if that is a billion or some very large number? We have this O of n kind of computational complexity just to compute the gradient. I'm not saying it's just O of n, but we have this loop in our code, looping over all the training examples at every iteration. I start here in parameter space. I have to compute the gradient. That involves looking at all training examples. OK, I go here. Now I have to find the gradient again. That involves looking over all training examples. So what we're going to do, and it sounds maybe not possible at first glance, is we're going to come up with an optimization algorithm that does not involve this loop over all training examples per iteration. And here's the algorithm. So we're cutting straight to the punchline today. The algorithm is, this may look, in fact, this looks extremely similar to gradient descent, except there's this tiny little letter I in blue, which is really the only difference between what you're seeing here and what I showed you before for gradient descent. And what does that little I mean? It means instead of taking all the training examples, instead of our gradient being a sum over all the training examples, let's just pick one training example at random and just say, pretend that's the only data I had, just this one point. And let's just use that to compute the gradient. And that immediately solves our problem of looping over n things and immediately introduces a big problem, which is this is no longer the gradient. What is this thing, right? It clearly doesn't reflect what all my data points think I should be doing. It's just what one data point thinks I should be doing. And so there's plenty to talk about today in terms of I think it's fairly clear to see why this is a good idea, but it takes longer to see why this isn't a horrible idea, in the sense that it's solving a problem but introducing uncertainty that we need to dig into. Okay, so that's what it is. And this is nothing new here. This is just saying the same thing we already said for gradient descent. The whole algorithm is we're going to start with some parameters. We're going to apply this update over and over again until we get to some termination criteria. Connor.
Is it a different training example at each iteration?
Yes. Is it a different training example at each iteration? Let's assume that at each iteration we're randomly picking a training example. Okay. Now we need to play some games to try to convince you that this is not a horrible idea. First thing we need to do is we've been talking since many weeks ago about this idea that we are allowed to multiply the loss function by a constant, and that doesn't change. In our optimization language, that changes the minimum of the loss, but not the minimizer of the loss, which is the thing we care about. We care about the W. So we added the 1/2. Sometimes I was sloppy and left out the 1/2. Whatever, you can multiply your loss by whatever you want. So in order to convince you stochastic gradient makes sense, I'm going to say let's multiply all our losses by 1 over n. That is not fundamentally changing anything we've been doing throughout the course. So we have our least squares, logistic regression, with regularization. And in general, we're going to be talking about losses of this form. And I haven't yet said why I'm going to do this. But first, I want you to agree that I'm allowed to do this without changing anything. Okay. Fine. Here's the way I like to think about this. What we have is we have some loss function, which I'm temporarily calling capital F. I guess we used to call it lowercase f, but I'm just temporarily calling it capital F to make it look more different visually from f sub I. The whole course we've been having losses that were of the form sum of some contribution for each training example. Now I'm saying we can have 1 over n. That's the same thing. And we need to talk about what the gradient of that thing is with respect to W. And it's the gradient, or it's a derivative of a sum of things. And we are allowed to interchange the sum and the derivative operators. So what it means is the gradient of the loss function is actually a sum of little gradients for each training example. And to me, at least, once I see this, I can start to be convinced that the stochastic gradient thing is not completely insane. Because actually the gradient can be interpreted now as 1 over n times the sum of these little gradients, each one coming from a training example. Or, in other words, the gradient is the average of the gradients that each point is contributing. So this point over here, and now again, we talked at the gradient descent lecture about this ability to switch in our minds between the data space and the parameter space, okay? So data point number 1, it lives somewhere in the data space, but in terms of parameter space, it says, go this way. That's the gradient. And the gradient also has a magnitude. It's not just the direction, but it says, here's my gradient if I get to make all the decisions around here. And the second data point in my data set says, oh, how about this? I have this gradient, maybe smaller magnitude in this direction. And the third point says, actually, the line is passing right through me, so my gradient is 0. I'm very happy. I already have no loss. And the fourth point says, I want to take a big step in that direction. And all what we've been doing with gradient descent for the last few weeks, actually without saying it, is we've been letting the overall gradient be the average of all of those things. And so it's kind of like a democracy, if that's helpful. So each point gets to say its piece, and then we're just averaging all those things. And now I'm coming and telling you, well, what we really want is an average of a bunch of numbers. Let me pick one of those numbers at random instead. I'm just going to pick one of those gradients out of the 500 gradients if n equals 500. And that's not that bad in the sense that what is the expected value of that thing in probability terms? It's just the average, right? So, so on average or in expectation, this is doing the right thing. Because if I pick a random number out of a group and do that 1 billion times, then on average I'm going to get the average of the numbers. Any thoughts on this? Yeah, Edwin.
Isn't it the case that you need a large number of samples in order for it to converge actually to the expectation? So if the number of iterations of the optimization is small, isn't it?
Yeah, so Edwin is saying, isn't it the case that you need to do that a bunch of times to get convergence to the average, and so if the number of iterations is small? So yes, thank you, that's true. So in general, in optimization, there is often a trade-off between how much effort am I going to spend per iteration and how many iterations do I need to do. If I work really hard per iteration, I might be able to converge in fewer iterations, and so it's not immediately obvious if that's a better method or a worse method, and it depends on the problem. And for those of you taking Computer Science 406, you're probably seeing some of these algorithms now, second-order methods that use the second derivative. You're doing more work, but they can converge super fast. So there's this spectrum in the field of optimization, and you could think of kind of heavier duty methods that we're not talking about in this course, and then gradient descent, and then stochastic gradient descent is way on this extreme, which is saying I'm going to do incredibly little amount of effort per iteration. In fact, if I have 1 million data points, 1 million times less work. So I'm going to expect to do more iterations. And I'm not saying that's a good thing. I mean, in answering your question, I'm saying it's a good thing. But I don't actually, I would love to just converge as fast as possible. But realistically, I am going to be doing a lot of iterations. And in particular, one thing we might want to ask ourselves is, how does the number of iterations compare to n? Because if the number of iterations is around n, then it's kind of like I've, on average, looked at every data point at least once, which is probably a good idea, right? So short answer, we're going to need to do more iterations. Nonetheless, we will have to be very careful to get this thing to converge. We'll have to be more careful than with regular gradient descent, but we're going to talk about it. You asked the question last time, but Cheyenne, yeah.
So the question is that we are taking one example, right?
Yeah.
And one example doesn't estimate the average properly. What if I was to like take 10% of a random sampling and then take the average?
So Cheyenne is asking, what if I take a subset but not all? And indeed, people do that all the time, and that's hopefully somewhere in the slides that are to come. So yeah, you can take a batch or mini batch, as it's sometimes called, of examples, like 5 examples at a time or 10 or whatever. And as you change that number, you're changing the slider, again, of work done per iteration and quality of your step, and therefore presumably number of iterations. And it's not like super obvious. It's not like you could just show me some data set and be like, Mike, I'm doing logistic regression on the data set. What's the best batch size I should use? I don't know. It's not super obvious to me, right? And so we can, again, think of this as another hyperparameter. And we can try we can try some preliminary experiments or playing around with the data or trying to understand what's a good value of that. Or we can just say, I'm going to treat this as a hyperparameter, just like any other hyperparameter, like my regularization, and not really worry about it. Or sometimes the hardware situation might actually dictate. Maybe there's some parallel hardware we want to take advantage of. And if I take a mini batch size of 32, I can somehow process that all at once. Whereas if I just take a mini batch size of 1, I'm wasting the capabilities of my hardware or something like that. Any other questions or comments? Okay, so I'm hoping your state of mind at this point is something like, yeah, that doesn't sound great to do this loop over n every time. It's going to save me a lot of time if I only pick one example or a small number. But is that going to have anything to do with stepping in the right direction? And now I've kind of argued that on average it's stepping in the right direction, even though a particular step might be a disaster. And in fact, an iteration is no longer guaranteed to decrease the loss for any step size, right? Because that one example might just be totally not on the same page as all the rest of them. It could be some crazy outlier or whatever. And so this whole process is going to be more noisy, but sort of a necessity. Okay, so this I think we talked about. So here's a kind of static picture. I have some demos that we can look at as well in a minute. So this is a picture of parameter space with two parameters, right? Parameter 1, parameter 2, the red thing being the minimum, those being the contours of the loss, and we're approaching the minimum. Okay, so let's look at some pictures. Let's consider the case where we have 5 training examples and we're minimizing squared error. And there is some optimal W, and we just have one variable W, simple case for illustration. And the loss looks like a parabola because we're using squared error. And then we start at some W0. And in these pictures, it's just one-dimensional, not even two-dimensional. So we're just moving along the single axis here, trying to get from where we're starting to W star, which is the best possible thing. So gradient descent says, well, what's the gradient? I compute it, it's positive. In this case, there's only 2 directions you could go, positive or negative, because we're in one dimension. It says go that way. Okay, I'm going to go that way. I'll compute the gradient again. It says go that way, so I'm going to go that way again, end at W2. Now I'm at W3, compute the gradient. It says go that way. Now maybe I cross over, so when I compute the gradient this time, it says go to the left. But eventually I'm converging to where I need to go. And unless my learning rate, alpha, is too big, the loss should be going down at every iteration. So here's what's happening with stochastic gradient. Each example has its own loss function. Each example has its own agenda, if you will, right? And that's what's being shown at the bottom. And the overall loss is the average of all of those losses. And again, there's 2 ways you can think of this, and I'm fine either way. You can think of it as I'm picking a random loss, or I'm picking a random gradient. So this illustration is the picking a random loss illustration. So at my first iteration, I'm going to randomly pick point number 2. And so I'm only seeing this loss, this parabola here. And it tells me, well, I'm way over there at W0. It tells me to go right. So that's good. And a piece of intuition, I think, is that when you start, your W is just randomly initialized, say. There's not much reason to believe your initial guess is that great. So maybe most of the examples would agree on roughly the direction you need to go in parameter space. And so why do I need to ask a million examples and have each one tell me roughly go this way? Any of those examples that I picked in this particular case would have told me move that way. And so why am I doing a loop? Well, over 5 isn't that bad, but over a big N is that bad. Why am I averaging everyone's opinion if everyone was going to tell me go that way anyways? That's another way to think about this. That no longer becomes true as I get close to the optimum, and then the different examples kind of start disagreeing with each other more. So that's what's happening here. We start at W0, we compute the gradient, tells us to go right, we go right. Now we pick a different random example. So now we're suddenly, if you will, minimizing a different loss, or taking a gradient with respect to a different loss. It again tells us to go that way. We pick another random example. And now look where we are. Here we're on W2. According to this parabola, to get to the minimum here, we need to go left. If I take the derivative only looking at example 1 wants to end up over here. So this is going to send me in the wrong direction. This is a way of thinking about how you might end up going in the wrong direction. If I had looked at all the examples, as in regular gradient descent, it would say keep going right. But because this one training example has its own loss, we end up going left. And then this repeats a bunch of times. And we hopefully eventually make progress. So this is, as I was saying before, there's some region of the space where every or most of the training examples will kind of say the same thing, and that's where these savings are really big, right? Because why look through all the examples? I'll just look at one, they'll get me to the right direction, and then there's this middle part where things are a little murkier. And I'll talk next about how to deal with this issue and actually get it to converge. Any thoughts on this? Arman? Okay.
So do we switch back and forth between stochastic and non-stochastic as we approach?
Yeah, this is a question I often get. Should we just switch into regular gradient descent at some point? It's a reasonable thought. A less dramatic version of that would be, why don't we increase the batch size over time? Because batch size equals n is gradient descent. So I actually have a slider between how close to full gradient descent is. So it turns out we actually don't even need to do that. It's a perfectly reasonable thought, but we can actually just keep doing what we're doing, and as we'll talk about in a minute, manage to converge even without doing that. But yes, that's a very reasonable thing to say. Okay, you can quantify how sort of confused you are by how far away the individual gradients are from the true gradient. So if this variance quantity here is 0, then it means all of the individual gradients equal the true gradient, and so I'm always going to go in the right direction. And when this quantity is very large, the variance of these individual gradients is very large, then it means I'm in this more confused state. Okay, so here comes the way to deal with this convergence issue, the step size. The punchline of what I'm about to say is that by decreasing the step size over time, then we can get SGD to converge. Whereas with regular gradient descent, we could keep the step size constant. And remember, the reason why that makes sense, does it say step size? Yeah. It's not my favorite word. Alpha, learning rate, we can call it alpha maybe. The thing is, as we talked about in the gradient descent lecture, the size of your step was getting smaller because the gradient magnitude was getting smaller, even if alpha was constant. But here, we actually want to make alpha itself smaller over time, which is why we've been writing alpha t this whole time in anticipation of wanting to change lambda across the iterations. Yeah, this is a bunch of words. I prefer the picture. Let's go to the picture. So here's where you start. Like, this is in some two-dimensional toy parameter space. Here's the solution. And here is a ball around the solution with radius alpha. And roughly, you can think about stochastic gradient descent as doing kind of reasonable progress towards the solution when I'm far away. And that's exactly what we've been talking about. Many of the training examples are aligned with each other, agree with each other. We're kind of getting there. But then when I get very close, crazy stuff happens. Because basically it's this variance thing again. The gradients are all different from each other. And so I'm just bouncing around the solution. And here's the thing. If we decrease alpha, if they're bouncing around a ball of size alpha, if we decrease alpha, then we're now bouncing around in a smaller ball. We don't want to start with alpha super tiny, because then this blue part at the beginning is going to take a really long time, tiny, tiny, tiny steps to even get close. But if we start with alpha being big, and of course the question is, how do we know when to decrease it at what rate? And those are realistic questions, but intuitively, this can get us there. And there are other ways we can improve things. So one thing I'll talk about in a minute is you can try averaging a bunch of your iterates. So you might be thinking all this red bouncing around, if I average all those points, they might land right on the center, and that's another type of strategy. Okay. Right. So I guess I kind of said this. We want alpha to shrink, not too slow, not too fast. So there's theory behind this. And the theory said that alpha should be sufficiently big that this sum is infinite. So if alpha is constant, then, well, that's definitely true, like if alpha is 1. But even if alpha is decreasing sufficiently slowly, that can still be true. But on the other hand, we want alpha to decrease sufficiently quickly. So this not too slow but not too fast has this theoretical backing. And for example, if you let alpha go down as 1 over t, so some integral, whatever, it's easier for me to think in terms of integrals. So the integral of 1 over t is going to go to infinity. And the integral of 1 over t squared is okay. It is finite, so this is all okay if I let alpha go down as 1 over t. So I'm not too concerned with the details here. I don't even know that many of the details. But I'm concerned with you understanding why the step size needs to decrease and what would go wrong if you decreased it too quickly or too slowly. So before you burn this 1 over t thing into your brains, sometimes theory and practice are not exactly aligned. So there's a whole bunch of different ways of decreasing alpha that people tend to do. You can shift the curve a little bit, which makes it not decrease so drastically at the beginning. Or you can even just use a function that doesn't satisfy those properties, and it might not be that bad. And the way to do that is this averaging that I mentioned. So if I'm bouncing around in this ball, if I just average all those iterates, then it should land sort of in the middle of the ball, which is where we're going. So I don't know if you feel like this every lecture, but for this lecture, you're very welcome to wish that you had Mark Schmidt, the other person who teaches this course, because he's a world expert on this stuff and one of the people who has invented a bunch of these algorithms, including these stochastic gradient with averaging algorithms. So even if he's not your instructor, there's really cutting edge work going on at UBC in this field. So optimization for machine learning, and now with very large data sets. Okay. So the picture is showing kind of idealized version, I guess, of what happens if you start taking the average of your iterates. Okay, so take-home messages here. It doesn't just work out of the box exactly like gradient descent does, although honestly, gradient descent, even though you can set alpha to be constant, it often isn't that great anyways, even with gradient descent. So you can just see the proliferation of hyperparameters starting in this course. And we're going to, by the end when we get to deep learning, there's going to be tons of hyperparameters. But okay, I'm using stochastic gradient descent. What should my mini batch size be? How should I decrease alpha over time? Maybe there's multiple hyperparameters associated with how I should decrease alpha over time. My initial alpha and the rate at which it decreases, et cetera, et cetera. Okay, I'm going to switch over to Jupyter. I'm excited about this demo, so I hope it works out. No surprises, hopefully. You're probably tired of me generating synthetic 1D data sets, but I mean, what can I do? I just can't draw things for you in 10 dimensions. So here's a made-up toy regression situation where we have one feature, x, and our target value, y. And it looks like there's a sort of line-type trend going through it. And I'm going to run gradient descent. So you can look at the code. I pick some alpha. I pick some number of iterations. I'm going to draw a picture at every iteration. And I showed you almost the exact same thing in the gradient descent lecture. But I'll get the derivatives, do these updates, and let's see how it looks. Looks pretty, yeah, I guess it's not that bad. Okay, so the main change between this and what I showed you in the gradient descent lecture was I improved the plotting code a little bit so you actually see the trace of all the steps instead of just the current location. So what is gradient descent going to do? Well, if you make alpha really small, it's going to do this nicer, kind of smoother getting to the minimum. If you make alpha larger, it might do some bouncing. We have a tiny bit of bouncing here. I would really encourage you to play around with this code after class, you can change all kinds of things, do more iterations, change alpha, change the problem, and just getting a sense for this, I think, is a useful thing to do. You can make alpha big and watch it blow up. I guess that would be fun. I don't know. Probably just go crazy. Yeah. Okay, that's good. Anyways, this is worth playing around with, but nothing new here because this is just gradient descent. But now I want to show you stochastic gradient. And you should be able more or less to read the code here. I mean, maybe not write it without looking at the documentation, but whoever needs to do that anyway. So what I'm doing is picking randomly some batch size number of points. So I think I set mini batch size to 2. So I'm picking 2 points at random. And then I'm just doing the exact same thing, getting the gradients. I'm in this case doing alpha over square root t, so I'm decreasing alpha over time with 1 over square root t. I guess 1 over t would be a little more correct, but what can you do? And then I'm plotting every 10 iterations. Okay, so here's how you should read these pictures. I'm plotting in red the points that were randomly chosen, basically the mini batch. So those 2 red points, those are 2 data points out of the n data points that were picked at random. And what I'm plotting here for you, maybe there's an off by 1 error that it's showing you 2 iterations instead of 1, but that's not a big deal. What I'm showing you here is what does the loss look like from the perspective of those 2 points that's picked. So I think a very important point that I forgot to say earlier is that SGD can make the loss go up. You might go in the wrong direction, but not only that, but you do not know that that just happened. Because you could say, oh, I'll just compute the loss before the step and compute the loss after the step, and I'll see that it went up. No, you won't do that, because computing the loss is exactly a loop over n things. Like to get this beautiful picture in the upper right, that's the actual loss. I had to do a loop over n to get that thing, right? So if you take a step, you're not going to know if the actual loss went up or down, because that would defeat the whole purpose of using stochastic gradient, which is that I do not want to sum over n things at every iteration. So you're kind of running around blind in a sense that you don't even know if you improved the loss or not when you took a step. Gareth?
Yep. Is there any benefit to computing the true loss at some set intervals numbers?
Yeah, there is benefit to computing the true loss at some set intervals, and sometimes even the validation error at the same time. Yeah. Okay, so I just ran this randomly. I guess it's doing something. Oh, I see. It's not plotting every iteration. Okay, that makes sense. So, fine, good. So what you can see here is, and you can play around this code, and you can play around with the mini batch size. You can make it 1, you can make it n, and you just try to think about, from the perspective of that subset of points, what does the loss landscape look like? And I'm taking a gradient step with respect to that loss landscape, and it may or may not actually point me in the right direction. So this is a very kind of toy problem, but it's sometimes still useful to play around with it. My main take-home message from making these demos for you guys is, wow, these things never actually work the first time. I always end up fiddling with the learning rate for 20 minutes to actually get it to do anything reasonable. And indeed, there are better ways of picking the learning rate than just making something up. There's all sorts of adaptive methods that tend to be pretty useful. Mohammed.
Does this mean if actually I have enough iterations, gradient descent, stochastic gradient descent will always converge to my minimum point?
If you have enough iterations and you're decreasing alpha in a way that you are supposed to be, like 1 over t, then you're going to converge, yes. And or using some other method, like some of these averaging things. Right.
And why can't you set n equals 1 in this case?
Yeah, I can. It just... I can set n equals 1. It's just that the losses are kind of weird looking when I set n equals 1 because there's actually a whole space of parameter values that will minimize the loss. Because if I'm only picking 1 point, then there's infinitely many lines that are going to perfectly pass through that point. So the losses, you basically get this line of minimum loss, and anything along there is going to get you 0 training error just with respect to that 1 point. And then, I don't know, I guess it's fine. I mean, the demo still works, but I thought it was prettier with 2 points. So I told myself at the beginning that if I had enough time, I would indulge myself in a story, and there seems to be enough time, so I'm going to do that. In my past life, I was a biophysicist, and there's a very interesting connection between that and what's going on here, which is that I was studying amoebas, and the way all these amoebas do is they basically look for food. And so if there's a food source over here, near the food source, the concentration of those food molecules is going to be very high, and then it decays away from the source of food. And all the amoeba is really trying to do is just eat as much as it can, and so it wants to move closer to the food source in a place where there's more food. And what it does is just kind of sitting around here, and it's basically counting how many food molecules are bouncing off the amoeba. And if it counts that, I don't know, 8 molecules show up on this side of the cell and 7 or 6 molecules show up on that side of the cell, it's like, oh, that probably means the food concentration is higher over here than over here, which probably means there's kind of a gradient in that direction, and let me move in that direction, and hopefully I'll get to eat more food that way. Seriously, this is how they work. So they're actually estimating a gradient. Really, they're kind of doing gradient ascent up the concentration, but they're measuring the gradient in a very noisy way because they're just counting a number of food molecules and there's Brownian motion going on, and that's not a super reliable estimate of the concentration, especially if the numbers are really small, like 5 molecules, not 5 million over here and 4 million over there, right? So there's this interesting trade-off that is kind of analogous to the mini batch size in the sense that the amoeba could do the following thing. It could sit here for half an hour and get a really good measurement and say there's 100 food molecules hit the right-hand side of the cell and 80 food molecules hit the left-hand side of the cell. I'm quite confident now that I should go that way. And so I'm spending more time estimating the gradient to get a higher fidelity direction and move in that direction. Or I could say, forget it, I'll just 2 over here, 3 over there, fine, I'll go this way, 3 here, 2 there, fine, I'll go that way, right? And it's a nice analogy. It's again this trade-off between how much time do I spend thinking about it, in that case integrating over how many molecules I see versus looping over my training examples, but it's really the same thing, versus do I just go somewhere, hope for the best, and do it so many times that I hope everything will kind of work out. Garrett?
Okay, so is the mini batch size the number of test examples that you're considering, or?
Not test examples, but training examples.
Examples, sorry.
The mini batch size is a number, an integer from 1 to n, 1 being the way I introduced it at the beginning of the lecture, and n being full gradient descent that I'm going to use. And here it's the number of red dots because I'm actually showing you the chosen examples for that iteration. Okay, thanks for indulging me with that. Okay, so to summarize, stochastic gradient minimizes the average of smooth functions. It's similar to gradient descent, which we've already talked about it. The reason why you would want to inflict this upon yourself is if n is very large. If n is 5, I'm not going to bother with this because it comes with all its extra baggage of having to deal with the learning rate and everything. And I might as well just do gradient descent, or maybe not even gradient descent. Arman?
Do the amoebas adjust their step size as they approach the food source?
Do the amoebas adjust the step size as they approach the food source? I have no idea. Yeah, it was a long time ago. Okay, and the kind of classic version is you pick one example at random, but you can pick some number greater than 1 examples, as we talked about. And I'd really like you to think about this trade-off between effort per iteration and quality of my iteration, thus determining the number of iterations that I'll have to end up doing. And there's some theory about these things, like how alpha should be decreased, but often you may want to play around maybe with a subset of your data to try to understand what works well for your problem or something like that. So this converges very slowly, which is just another way of saying you need more iterations to get where you're going. And there's all kinds of tricks you can do to speed this thing up. And a lot of advances in deep learning lately are variants of stochastic gradient descent that work a little better, and then everyone adopts that because stochastic gradient descent is particularly popular, as I was saying, in the deep learning community, and we'll get to that in a few weeks. So there's also other kinds of tricks aside from decreasing the learning rate, such as averaging. Okay. We didn't do the first one. Just a minute. Okay, so we talked about stochastic gradient, also known as stochastic gradient descent, also known as SGD, or maybe just SG. Can't live with it, can't live without it, right? You need to do this if you have giant data sets, but you have to deal with all the implications and be careful about the learning rate. And stochastic average gradient and some of these other recent improvements make it work a lot better. So that's it for today, and I'll see you on Friday.